Hi, I'm Vindula and my partner is Tavishi, and we are here to present human-compatible Eco-Lagrangian control at signalized intersections. Greenhouse gas emission levels and fuel consumption rates have been steadily rising, and the transportation sector in particular contributes 29%. Human driving at signalized intersections often creates shockwaves, causing high fuel consumption and emission, which call for energy-efficient driving strategies known as Eco-Lagrangian control or eco-driving. Most work that studies eco-driving assumes a fleet of autonomous vehicles to carry out these strategies. However, fully autonomous vehicles are predicted to take more than another decade before they become widely adopted. A promising near-future solution is to generate human-compatible structured policies which humans can follow and execute. These policies should contain a simple action space, and any targeted action must be maintained for a fixed amount of time steps.
Our objective of this project is to design eco-driving policies for when a vehicle approaches and leaves a signalized intersection. We look at two types of control policies, one for autonomous vehicles and the other for vehicles driven by humans who can execute a given set of instructions. In both cases, our overall objective is to reduce fuel consumption, carbon dioxide levels, and travel times. Additionally, the policies designed for human drivers should maintain human compatibility. We look at a platoon of vehicles approaching and leaving a signalized intersection that is led by a controlled vehicle. We simplify the vehicle dynamics to be the equations of motion, consider the state to be the position and velocity of the leading vehicle, and the control action to be the longitudinal acceleration.
Including the discrete dynamics of the traffic signal in our optimization can make the problem too computationally expensive for real-time execution. Therefore, we design our control algorithm based on the observation that idling at intersection can cause higher fuel usage and emission levels. We define two model predictive control methods based on the condition of whether the approaching vehicle can cross the intersection without stopping in its current speed. We define these two control models as MPC-NTL and MPC-TL. Our MPC-NTL model assumes that the vehicle can cross the intersection without stopping and therefore contains no constraints related to the traffic signal dynamics. Then our objective is to reduce fuel consumption while increasing the travel speed subject to the vehicle dynamics, initial conditions, and the state and input constraints. In contrast, when the vehicle is expected to stop at the intersection due to the traffic signal, we use MPC-TL. Here we set an extra constraint to the MPC-NTL such that the vehicle should travel at a non-zero velocity at the stop line of the intersection. Next, we extend our two MPC models with human-compatible constraints. We require each action to be maintained for a delta amount of time steps, making the resultant policy a zero-hole policy.
Here we can see our simulations. We use a baseline IDM model to imitate realistic human driving behaviors. As can be seen in the first video, the vehicles stop at the intersection, creating stop-and-go waves. The same behavior can be seen in the time-space diagram on the right. In the second video, where the autonomous vehicle leads, we see that the vehicles do not stop at the intersection, but rather just cruise through. Similarly, under the human-compatible driving policy, we see a no-stop behavior. Here on the left, we see the expected piecewise constant acceleration profile of the human-compatible driving policy. In contrast, the CAV-compatible acceleration profile looks more irregular. On the right, we see the speed profile of the leading vehicle showing a non-zero speed at all times for human-compatible driving. Next, we also look at the trade-offs to be considered when designing human-compatible driving by varying the action extension delta parameter. In summary, if the delta is too large, both fuel consumption and travel speed can be significantly worse than human driving. We recommend practitioners find the optimal delta value that provides the best benefits under human compatibility constraints. One possible direction for future work is to include inter-vehicle dynamics and explicitly model the traffic signal dynamics in the control problem. Extending the optimization problem to multiple intersections is also an interesting direction. Thank you.